organizers. Actually, this guy is out of control here, Lucas, and we spent the weekend flying around the beaches of Brazil in these machines. So, I mean, it's only in Brazil you get this type of hospitality from the conference organizers. For those of you that don't know it, I mean, Trinity College Dublin is sort of right in the center of Ireland's capital. It's a very nice place. Some of you maybe have been there as a tourist before. This is the old library. This lecture hall here is the Schrödinger lecture hall, and essentially it's famous because essentially it was the lecture hall that Schrödinger gave these very influential lectures of what is life. So this year we had the 75th anniversary, and in fact there wasn't a single physicist there, so it was only biologists at this thing. And actually this talk is sort of interesting because I mean, in some ways it took some inspiration from biology. Okay, so essentially the group in Dublin consists of a number of different people. Giacomo, who's a postdoc, will present on Wednesday, and Cecilia has a poster here, so please check them out. This work is essentially along with some collaborators. This is Gabriel Landi, who's here, Stephen Clark from Bristol, who's a long-term collaborator of mine, and the main hero of the story is Giacomo Guarneri, and I'm sure he could actually give this talk a lot better than I could. So, I mean, if you want to talk in a little bit more detail about what I'll tell you about, we can chat at any point. Okay, so let me just quickly outline the talk. Hopefully I can get through most of it, and if not, well, I can tell you more later. So I want to tell you a little bit about this idea of thermodynamics of precision, which is an idea coming from more like the classical stat-mech community, and a generalization to what we're doing is trying to generalize it more generally to the quantum mechanical evolution. It's a sort of statement on entropy production, and it's related to entropy production in non-equilibrium steady states. I'm going to tell you a little bit about that in a second, and I'll sort of motivate the main result. And I think crucially, even though the result it's proved in a rather technical way, the main result essentially is very straightforward to understand, and it has, in my opinion, like a profound implication for the performance of autonomous thermal machines. All right, so what do I mean when I talk about a non-equilibrium steady state? So just so we're on the same page, what you can have in mind for the purpose of this talk is essentially some mesoscopic or nanoscopic conductor wedged between, say, metallic leads at different temperatures and different chemical potentials. And essentially what you're thinking about now is the long time limit, and essentially the thermodynamics there is that this type of non-equilibrium steady state supports macroscopic currents, so charge currents and an energy current connected to the conserved quantities, and these currents sort of are mediated by the so-called thermodynamic forces, delta beta mu and delta beta. So we believe that this is positive on average, and that's sort of the thermodynamic scenario. So it's connected to conserved currents in this conductor. This is very different to the standard equilibrium state, of course, where everything just reaches the same temperature in the infinite time limit. But one of the things that, I mean, essentially is central to this talk is the fact that in this non-equilibrium steady state, I mean, currents, they fluctuate about their average value. They have some variance. So if you really take the long time limit up to which the system reaches the non-equilibrium steady state, then for all times afterwards, you'll see that the currents fluctuate about their average value. And essentially, the results on precision are connected to this. Essentially, precision means keeping this current fluctuation small. Okay? So that's the setting. Motivations, well, for studying non-equilibrium steady states in general, they're sort of central to many different fancy areas beyond kind of mesoscopic physics. So you can think about sort of exciton transport in photosynthetic complexes. You can think about sort of nano-junction thermoelectrics or single molecule electronics. Phononics, so controlling heat flow to do the things that you typically expect in electronics. And in the classical domain, they're very important for the physics of biomolecular motors. Okay, so non-equilibrium steady states in general are interesting to study. Heading towards the sort of quantum domain, there's some beautiful experiments which I think are well worth pointing out. So this is an experiment in the group of Tillman Esslinger in cold atoms. So what they do there is essentially they have two degenerate Fermi gases at different temperatures and different chemical potentials. And essentially it's one of the first times that DC transport has been measured in a cold atom setup. So what they can do is they can count essentially the number difference between these wells and build up essentially current information. So to provide a type of thermoelectric simulator, that was the sort of main goal. There's other experiments in optomechanics, cavity BECs, and this one in particular is very nice. So in the mesoscopics community, they recently built in the Heine Linke group in Lund, essentially a single quantum dot heat engine wedged between metallic contacts. I think, although they've been studying current fluctuations and currents for 20s of years in this community, what's quite new is the ability now to measure sort of heat currents. I think it's quite exciting for thermodynamics. Okay, so what is this idea of thermodynamics of precision? Well, I first kind of came across it a couple of years ago when I was reading through classical literature. You see many results and stating this thing of thermodynamic uncertainty relation, and of course I was asking myself, what is this? So the idea originally came from Udo Seifert's group in Stuttgart, and then was quickly followed by let's say, a more rigorous paper in the group of Germany, England, and MIT. So these guys essentially are, stat mech people that are very interested in biological processes. Let me just give you the statement of the thermodynamic uncertainty relation. So essentially this comes from Seifert's paper. So the idea is that a sort of chemical reactions which are catalyzed by enzymes, these are kind of centrally important to many cellular processes, like, for example, a biomolecular motor. There are these objects which sort of walk along filaments, and they can be modeled by a bias random walk. So the way you model this is with a classical Markov process. So you let X alpha be the output of some chemical reaction, and then you can define a current as just, say, this output divided by time. And what they do then is they define a kind of normalized variance of the current. So the fluctuations of a particular current, it could be the current of particles, the current of output of a certain chemical reaction. And the entropy production rate is the sum of the currents times their thermodynamic affinity. And what Seifert and Barato showed essentially was this very, very interesting relationship. So for any classical Markov process, the average entropy production rate in the non-equilibrium steady state is bounded by below in a term which is the inverse of those current fluctuations. So what does it mean? It means that if you want very, very good precision, if you want to keep the fluctuations of a current low, then you do this at a cost of entropy, of dissipation, okay? So more precision means more dissipation. This relation shows this for classical Markov processes, and sort of what I was inspired by was to see how general this relation is. Like, is this somehow a more general result in thermodynamics beyond the classical Markovian paradigm? And then what is the consequence for sort of thermal machines and technologies if it is true? So that's the sort of the setting. Okay, so how do we do this? So your first bet might be to try to sort of do what Seifert did, but with a quantum master equation rather than a classical master equation. But for multiple bats, quantum master equations are problematic for reasons that I don't want to get into. So actually, around the same time, I was sort of studying some very old book on statistical mechanics by a Russian called Zuberev. And Zuberev was a student of Bogolyubov. And essentially, if you look in this work, what he did was something quite remarkable, which is essentially he proposed a non-equilibrium ensemble for a non-equilibrium steady state. Just in the way we have the canonical ensemble in equilibrium, he was proposing essentially that you could write down directly an ensemble for a non-equilibrium steady state situation, whereby now you have Lagrange multipliers, which are not just the temperature and the chemical potential, but also the thermodynamic forces which drive the conserved currents, okay? So I'm going to take you through the motivation for this. There's nothing new in it. You can see it in an easier way. The setup we have in mind is the following. So imagine I take some quantum meso or nanoscale conductor, and I wedge it between two semi-infinite fermionic leads. So the idea of having semi-infinite leads is very important here. What I can do is I can take the Hamiltonian of the entire thing, so including the Hamiltonian of the left lead, Hamiltonian of the right lead, and the Hamiltonian of the central conductor. And what I do is I lump everything non-trivial in interactions in one term, okay, and everything free in the other. So these are the free Hamiltonians of the central conductor, the lead, the left lead, and the right lead, and so on. Initial condition is crucial, so I assume that these semi-infinite fermionic leads are prepared in grand canonical ensembles at different chemicals and different chemical potentials and different temperatures, and I can take an arbitrary system state for the central conductor, okay? So that's the initial condition. So the idea is then you take the long time limit, okay? And how is this done from a mathematical perspective? Well, what you do is what's typical in scattering theory is that you move to the interaction picture and you ask what is the sort of infinite time expectation value of observables, okay? So you define interaction picture evolution on the initial state, and then you take essentially the long time limit. So what you imagine is that initial time is minus infinity, okay? T is equal to 0, you've reached the non-equilibrium steady state, and after that time, then you're in the non-equilibrium steady state. So it turns out that, for those of you who might know some scattering theory, you can sort of express any sort of operator, its forward time evolution in the interaction picture by the so-called Euler operators, okay, which are connected to this interaction picture. And what's important is that you sort of do an adiabatic switching on of the interaction. So you have your initial condition, and then you slowly turn on the interaction between the leads and the central system. Okay, that's described by this exponential and the small epsilon parameter. And then you can show that these Euler operators essentially are the limit of epsilon goes to 0 of the interaction picture. Okay, this is textbook stuff, which is equivalent to Gell-Mann-Low theorem in scattering theory, for those who know, but it's not so important for what I want to do. The most important point is that they have this remarkable property, which is essentially you can take the initial Hamiltonian, okay, and you can basically take it, you can take application of these Euler operators essentially gives you the final Hamiltonian. So they are operators which switch forward between minus infinity and t equal to 0. And so then Zubrev's calculation in the book, okay, is essentially about taking this limit as epsilon goes to 0. That's essentially the idea. So how does that work? Well, it's just by algebra of these Euler operators. So if you go through the algebra, I want to go super quickly here because I don't have so much time. You find if you work through it, you can get rid of the initial state dependence. You can gauge it out because this is a non-equilibrium steady state, and you get back essentially a distribution which looks like this. Okay, let me explain to you what Z plus and H plus notation is here. So in the end, after you tidy this thing up, you find that this ensemble, which describes the non-equilibrium steady state, is a generalized Gibbs ensemble, where you have an additional operator, which is called the statistical operator. Now, what is this sigma hat? Sigma hat is connected to essentially the charges, which are then forward evolved in time under the Euler operators. Okay, and it's quite interesting because essentially beta hat, is the average temperature between the two leads. Mu hat is not the average temperature, yeah, it's the average temperature. Mu hat is the average thermodynamic force. And then essentially you get this term, and this term is nothing more than something which sort of depends on the conserved quantities and their corresponding Lagrange multipliers. So Zubrev's realization was that the non-equilibrium steady state of the whole thing, not just the central system, but of the whole thing, is a generalized Gibbs ensemble where you have an additional set of constraints because you have conserved quantities at the infinite time limit. Okay. Let me skip this. What's the interpretation of this thing? As I was saying, it has the structure of a generalized Gibbs state, just like the type of generalized Gibbs ensembles used to describe the long time limit of integrable systems. So sigma hat is itself a conserved quantity. So what I can do is I can rewrite the non-equilibrium steady state by basically taking this out of the exponential, okay? And what I'm left over is a very curious expression. I've rewritten the thing so that it sort of depends on this following state, which I call rho local equilibrium state, rho less. And rho less is sort of the state you would get if the central conductor reached thermal equilibrium with the leads at the same average temperature and average chemical potential. So I can rewrite it in this form. Why am I doing that? We'll come to it. So essentially, this thing is this local equilibrium steady state when essentially thermodynamic forces are set to 0. The interpretation, one thing you can check mathematically is that, well, if I take the limit as t goes to infinity of 1 over t of this thing, I get back the standard expression for entropy production rate that you expect from non-equilibrium statistical mechanics. So it's a tool that you can use to describe non-equilibrium steady states. It's very close to the Keldysh formalism of scattering theory. And one of the nice features of the thing is essentially if you take sort of derivatives with respect to the thermodynamic forces of the effective partition function of this ensemble, then these give you back the current and its fluctuations, just like derivatives of the partition function with respect to temperature give you back the energy and the energy fluctuations that you expect from the canonical ensemble. So it's pretty consistent. It's, from an operational perspective, not very useful because it's very difficult to do calculations with it, but it can allow you to prove a theorem, okay? So so far I've said nothing new, but I just wanted to motivate this sort of ensemble, this generalized Gibbs ensemble. Now the next thing I want to do is I want to see something, which is I want to write this entropy production, average entropy production, as a relative entropy. So many of you already know what a relative entropy is. Essentially, the classical version, it just sort of tells you the difference between two probability distributions, how different they are, whereas the quantum version tells you how different two density matrices are. And so what did we find? Well, we found the following. If you actually take, since rho ness and rho less, and I've written rho ness in this peculiar form, since they're actually diagonal in the same basis, I can easily take the relative entropy, and I get this very nice expression. So it's the average entropy production is equal to the relative entropy between the non-equilibrium steady state and essentially this state in thermal equilibrium, plus this term in delta phi, okay, which is like essentially an effective difference in the free energies of these ensembles, okay? So this is the difference of mass U potentials, so to say. What does this term mean? It's very clear what this term means. It just gives you how far the non-equilibrium state is from this equilibrium state. What does this term mean? We have to check first if it's positive, because this thing should be positive, because the relative entropy is surely positive, and we expect the entropy production to be positive. Actually, what Giacomo found, and I found this quite interesting, was that it's actually related to sort of noise in the equilibrium state. So if you take a first-order expansion of this term, what you find if the two leads are at the same temperature but different chemical potentials, that this term is actually the Johnson-Nisk noise, which is sort of famous in conductors. But the higher order terms are connected to higher order fluctuations of the equilibrium fluctuations of currents, okay? So this is the first sort of result, and now what I want to do is I want to go back to Seifert's original paper and try to prove the equivalent, okay? So what we do here essentially is we adopt a sort of geometrical picture. So there's a very beautiful paper from around 2007 by Gavin Crooks, which shows that essentially if you have a generalized Gibbs ensemble, so I use upstairs, downstairs summation convention here, lambda I are, say, Lagrange multipliers and xi are conserved quantities. What Crooks was interested was in the sort of geometry that this state space gives you. Okay, it's a Riemannian geometry, and he was interested in the geodesics in that geometry to try and find the paths of minimum dissipation. But because essentially this non-equilibrium ensemble is in this class, you can play the same geometrical trick here. So what I want to do is I want to analyze now the geometry that's sort of generated by this class of non-equilibrium steady states. So one of the nice things, of course, is that this manifold has got a metric, and essentially locally the relative entropy is connected to the Fisher information metric, so at second order expansion. Great. Now, what am I doing from here? Well, what I can do is I can get a bound, right? Because Fisher information has got a bound, a Cramer-Rao bound. And here I'll be interested not in the, say, estimating the parameter, but estimating a function of the parameters, which are going to be the currents. Okay, that's how I'm going to connect to the currents and their fluctuations. So this is sort of the mathematical machinery that we're going to use. And if you go through it correctly, what you can see is that local equilibrium steady state essentially also lies on this manifold because it's connected to the vector of Lagrange multipliers when I set those thermodynamic forces equal to 0. Whereas delta lambda is just going to be, I'm just going to slowly turn on essentially delta beta and delta beta mu. And if you do this, essentially what I'm interested in is estimating the currents, okay? So this is the sort of thing I want to look at. And what you find is essentially a new what I call a quantum thermodynamic uncertainty relation, which is actually related to the covariance of the currents, okay? So if you want the diagonal part of this thing, okay, looks exactly like the bound that Seifert described. Now what we were very excited about here is essentially that we didn't use any sort of dynamical assumption, so we neither used a classical assumption nor anything particularly Markovian. It was just a consequence of the geometry generated by this class of non-equilibrium ensembles, okay? What you notice here is that it's a factor of 4 looser than Cypher's bound. So this is a theorem, the second result. And now the point is, so what? Yeah, I mean, I've told you something about this thing is connected to, you pay more in dissipation if you want to keep your fluctuations low. But we're going to see that these things are actually extremely interesting from the perspective of applying this to a thermal machine, okay? So this relationship, now what I'm going to show you is that this is really important for an autonomous thermal machine. So actually it was sort of illuminating to me because I mean, in the literature you'll find a number of papers which state that there are situations where you can approach Carnot efficiency at finite power. So I just mentioned these two, but there are many others by Levidian and also the one by Campisi and Fazio. So their point here was that if you use a critical working medium, yeah, then you can approach Carnot efficiency at finite power. And I always wondered why, right? And I think this precision thing really explains why. So first thing, think in terms of some thermoelectric machine, okay? So what the name of the game is in thermoelectrics is that essentially you want to start the left lead in a lower chemical potential than the right lead, and you want to drive electrons with a thermal current against the potential difference, okay? And this is going to give you a power, which is just the voltage times the charge current, which is just equivalent by conservation to the left heat current minus the right current. So that's how you define the power. The efficiency of any thermoelectric device is going to be the power divided by the heat coming from the hot side. And essentially the average entropy production rate is just the difference of the right current over the temperature of the right side minus the current on the left divided by the temperature on the left. And so with a bit of rewriting, you can see that you can reformulate this in terms of the average power, something which is the Carnot efficiency, which is 1 minus the ratio of the temperatures over eta. And now you can apply the bound, okay? Because the power is a current. It's just the difference of two currents. It's equivalent to the particle current in this case. And Seifert found, essentially, the following bound on power. It's a universal upper bound on power for any autonomous thermal machine, which is described by a classical Markov process, which basically bounds from above the power of an autonomous machine by the fluctuations of the power. And it's very interesting because what you see here, if you want to go close to Carnot at finite power output, then the only way you can do this is if you make your fluctuations diverge, which would be the case, for example, if you had a critical system. So it really explains that the fluctuations are important. You can make a very efficient device with a finite power output, but you're going to pay in terms of fluctuations of the current. Now, what's the repercussion for our bound? Well, it's just basically the upper bound now is 4 times looser, okay? And that's great for us. You might say, why am I happy about a looser bound? But of course, our theorem doesn't really rely on a classical Markovian assumption. And in principle, it does allow you, if you go beyond the classical Markovian paradigm, to have a power which is greater than what you would have with a classical one. This is a conjecture. I haven't proved it. So my conjecture is somehow that if you have coherences in the non-equilibrium steady state, then in fact, you should go towards this upper bound, okay? It also explains two weird results, well, not weird results, good results in the literature, which have basically applied Seifert's bound to quantum mechanical scenarios, right? And they found violations. But this is not surprising, since they found the violations in regimes where essentially the system had coherences in the energy eigenbasis. So if you actually go through what they did, they were looking at sort of double quantum dot setups, fermionic leads, linear coupling, everything is quadratic in fermions, so it's super easy to work with some scattering theory for that. And okay, I don't want to get into details, we redid their calculations, and what you find essentially is that the region where they violate Seifert's bound is where you expect it to violate Seifert's bound, where you have essentially, degeneracies in the energies of the dots, where you expect coherences in the steady state. So there's a weak violation of Seifert's bound, which of course is fine for us. Our bound encapsulates that process. So essentially, that's the story. That in principle we have an upper bound now, which in principle you could try and saturate, even though we haven't really found a system yet that would saturate that bound. But it's a theorem, so I mean it would be nice to try and understand what's really the reason for you to have like a looser upper bound in the power of a thermal machine as opposed to a classical Markovian setup. So in summary, and I didn't mention this, essentially we also have the full covariance of the currents, which is something that's not done for the classical case as far as I know. Maybe there is some papers, I don't know. Which means essentially there are cross terms. You have new sets of bounds which we haven't explored. We were just interested in the diagonal of the covariance, okay? And the major point here is that basically what we'd like to do is we'd like to try and understand if there's some quantitative role of coherence in this violation of the Seifert bound based on the fact that essentially, I mean, you cannot have coherences in his setup, right? And currently we're looking into applying this to a few new models. So the summary from the perspective of theory is that these thermodynamic uncertainty relations are not a consequence of just having a classical Markovian process. They are a deep consequence of the structure of thermodynamics, the geometry of thermodynamic states. So that's essentially the punchline. So thanks for your attention, and I'll take questions.
Questions?
Thank you. In quantum mechanics, uncertainty relations are under appropriate